All right, our final speaker is Zhang Jiang from the Advanced Photon Source. Zhang obtained his PhD in physics from UCSD in 2007 under Sunny, and he did his postdoc at Argonne, and where he's the staff scientist now. And his main research interest focuses on structure, kinetics, and dynamics at the surfaces and interfaces of polymers, biomembranes, and then nanocomposites with nanoparticles. And today he's going to talk about coherent surface scattering imaging at APS-U for 3D mesoscale structures at surfaces and interfaces. I think you have to go into the Zoom.
Oh, okay.
So that the people can, the online can.
Okay, you don't use Zoom. Where is that point again?
Interaction and then
okay, well, great. Okay, thank you. I want to thank the organizer for inviting me to be here. It's very nice to be back to meet the older friends and enjoying the nice weather here. Okay, so I'm a beamline scientist at the APS, and you all heard recently we made a milestone. So we got the first light into the ring, and some of the beamlines also got light into their experimental hutch. And for the featured beamline, you probably heard there are a couple of featured beamlines. I was helping one of them to do scientific technical commissioning and scientific commissioning. And this is XPCS. I cannot talk too much because you probably have to read the news on the release, but I can say 48 hours ago, we got the first spectral pattern on this beamline. Very nice. So so basically the beam is back. So yeah, okay. Beam is back. I was supposed to be in a photo yesterday afternoon, but I have to come here, so I missed that. So anyway, so okay, I'm not going to talk about the XPCS. I'm basically responsible for the exotic technique called the coherent surface scattering imaging. You probably never heard of this. Some of you probably heard of that, but this is a recently developed technique. And this work was not done, of course, not in the APS-U. It's before XPCS-U. A lot of people contributed to this project, and this is the incomplete list of all the people. A lot of more people over here. And yeah, so the experience and knowledge we learned before APS-U actually help us design and construct this new CSSI beamline. Okay, so before I go to the technical details, I want to share some fundamental concept about the CSSI. This CSSI actually is not a single technique. It's basically a group of techniques that takes advantage of two methods: gradient incident X-ray scattering and coherent X-ray diffraction imaging. So it's basically nothing else than extending the transmission coherent imaging techniques to the gradient incident geometry. So basically, you can do ptychography, CDI. Those are coherent technique and coherent imaging method from the surface. So hopefully, we can, construct a three-dimensional, heterogeneous structures on the surface or embedded underneath the surface or in the thin films. So, so just start from some conventional, CDI ptychography concept, and using that you have a coherent beam. If your sample is smaller than the beam, then this you call that a CDI. And if your sample is larger than the beam, coherent beam, you have to do a raster scans of the sample. You use this, a lot of, convention, a lot of like iterative reconstruction algorithm. This is in the transmission geometry. And also recently, and if you want to, of course, CDI ptychography typically for single shot reconstruction. Single shot, I mean, you don't change the angles. Basically, what you get is a two-dimensional projected imaging, which I'll come to that concept later. And if you want to get a three-dimensional imaging, you can combine ptychography scans and tomography scans. People usually call that, I think, laminography. And we can do all this type of, experiments in the surface, geometry or gradient incident geometry. So, so why do we do that? Because I'm from this GSAX GWAX community. So, so a long-term problem in GSAX is the information you get from sample, the typical statistical average. So what I mean is typically your beam is incoherent or partially coherent, your sample is has a lot of random structure in there. It's like act like a scrambles, scramblers of the coherence of the beam. So eventually, what you get is basically a statistically enriched information. So you don't know exactly where the features are on the sample. So typically, you have to model the samples. When I say model, the structure factor, form factor, right? You calculate them, then you enrich over area or over time scale and to get information. But these are statistically enriched. But CSSI is basically you take advantage of coherent diffraction imaging method plus its iterative reconstruction algorithm. You can get an exact structure on the surface instead of statistically enriched information. So potential applications is for any kind of hierarchical mesoscopic structure on the surface. So this can include self-assembly on the mesoscopic scales, thin film, quantum dot growth, or nano patterns. And recently, you can apply this to critical dimension metrology, for semiconductor samples. So the very first CSSI experiment was done almost 10 years ago. So I don't want to talk too much here, but basically is we have a small sample. This is in a CDI geometry. Sample is smaller than the footprint of the beam on the surface. So the beam come onto the surface, and we measure the reflected signals in a small angle regime. And a single shot reconstruction. By single shot, I mean we don't change the angle, we don't scan. The single shot reconstruction gives you a two-dimensional projection, but doesn't have the surface, information about the implant on the surface, but doesn't tell you the third dimension. So, but you can rocket the sample, like rocket incident angles, right? You can construct a three-dimensional reciprocal space. Then you do, conventional, phase iterative algorithm on that. You can get a three-dimensional structures. I think this is the movie. Sure. It doesn't play, but anyway, the convergence is really fast. Okay, so so the resolution at that time is pretty bad. We have very crappy detectors, very low energy, very low flux. So, but anyway, in addition to the CDI scheme, you can also do CSSI at other modes. For example, you can do it in the ptychography mode for extended objects on the surface. You can do tomography too. In the rotated sample, you can get isotopic resolutions, and you can do multimodal too. For example, you can combine with holography, or you do some fluorescence experiment we actually did a couple of years back, and a lot of more possibilities here. So just first, I want to talk about the CSSI in terms of the holography concept. So we all know Young's slit experiments. It's a standard to demonstrate the wave nature of light, right? So from this interference patterns, the intensity, spatial intensity distributions, you can back calculate exactly what the dimensions of your slit or the sample, or whatever, in the length scales that you are interested in. And there is another concept, another method called Lloyd mirror. I don't know how many of you heard of that. It's alternative of Young's slit experiments, but in a reflection geometry, and you don't have to have any sample, just a flat mirror. That's it. So you can create this double slit patterns. The concept is basically you have the real source coming at the sample, or the flat mirror, the grazing incidence. So the directed beam and the reflected beam, basically you can view this as the virtual source. Right? So these two beams interfere with each other, can cause this intensity variation on the detector. So this was actually discovered 196 years ago in 1830. It has a bunch of applications nowadays. For example, you use this in the UV photolithography. And it has this method has the advantage of using regular like a photo mask, because if you use like a slit to do lithography, if you want to make a small feature, you have to increase the slit distances, right? By that you lose a lot of flux, so the power is low. But with this, the only thing you need to do to make small feature just raise the source height to keep all the power. So this is an advantage. Another application of this is basically, I think even astronomers use that. So to measure the the radio source in the galaxy. So I think a bunch of years ago they did this in the Indian Ocean or somewhere. So at a high elevated location, they measure the interference pattern directly from the outer space and the signal reflected from ocean surface. you have the interference pattern, you can calculate the direction. Basically, you calculate the angles. They can find where the direction of the radio source in the galaxy. So it has a lot of applications, but to see this in X-ray is not easy. So as you can imagine, to get a coherent X-ray is very hard. I mean, in the old days, and also to have a very flat mirror is not easy in the old days. But now it is possible. So that's what we did recently. So, but we call that a holography here because we indirectly demonstrate Lloyd mirror in the X-ray, a hard X-ray regime. So basically what you have is you have a sample, an object, nano object on the surface, and you have incident beam coming at an angle. So the directly scattered beam from the sample and the scattered signal and reflected again from the mirror, which basically we have only a silicon substrate, that's it. So these two beams actually interfere on the detector. It created a Lloyd mirror-like effect on the detector. So so this is what we observe. I mean, the sample is basically a grating, just a single line. It's not a regular grating, it's just a single rectangular line on the silicon substrate. And you can imagine that if the beam coming along the line, you will see an arc. If you do grating experiment, you will know that you see an arc. So if you get close to these angles that is below Curry angle of the, here is the silicon, which is for this energy 0.25 degree. And you can see we have interference, this oscillating signal over here. This is basically Lloyd mirror effect. Okay. And we actually have the simple calculation, use the holography method to calculate. This is our calculation to match experimental data pretty well. But if you don't, this is basically nothing else than a multi-beam effect. You probably know that. Or some people call it dynamic effect, but it's basically a multi-beam effect. So if you don't assume this kind of, virtual source, it's actually a virtual object, inverted object, you won't be able to simulate the experimental results. And you use a conventional kinetic approximations with no multi-beam effect, that's what you get. So, well, this sounds boring, right? What do you do with this? Actually, it has some application that I will show you next slide. So this is this is the first application. Basically, I will say demonstration. So what do we do here is we have a stacked samples over here, two lines. So the second line, the first line is basically 50 nanometer. The second line is about 35 nanometer. And this is the top view over here. So X-ray coming this way. Okay, so this is experimental data. I cropped the rest of the image, only left this, this Lloyd mirror effect region. And as you know that if these two lines stacked perfectly without any orientation errors, you would expect a single arc, maybe with some high order, fringes here along this transverse direction, which are the first order, second order, third order. So that's what you expect. But for this sample, we find that there are basically two arcs. It's not clear, but if you change the contrast, you see clearly two arcs. Originally, we thought, because this is like a crappy image, right? We saw that all the time where you have a bad slit or parasitic scattering, right? But we repeat the experiment again and again, we always got this. It doesn't matter how we do with the slits. So that's actually puzzles us for a while. Then realize this could be a Lloyd mirror effect. Actually, you are looking at two different, the pattern with two different orientations. So as you know that if you rotate the grating, the arc gonna shift. You know that, right? So these two lines actually exactly correspond to the misalignment of the stacked, lines. So actually, and with this X-ray Lloyd, mirror effect, we can calibrate the misalignment. It's very accurate. It's 0.09. This is basically induced. This is lithography made samples. So when we made a second layer, they cannot align these two patterns really well, in the E-beam lithography. So there was small misalignment, but we are able to catch that. It will be difficult to find this in SEM or AFM, but we can do that with X-rays. So this is our simulation. This is the line cut and simulations. Okay, so I go to the second mode of the CSSI, which we call that hard X-ray ptychography reflectometry. It's something related to ptychography plus reflectivity. I don't know, probably everybody here in Zoom heard of reflectivity, right? You have an incident beam, you have an accident beam. You track the two, beams while keeping the incident angle equal to the accident angle, and the intensity will give you reflectivity. It tells you the structure is perpendicular to the film or to the surface. But this technique doesn't give you any in-plane resolution because you only track the at the specular, where you only have QZ information. There are no in-plane Q information in there. So, but anyway, so in here, we found out that if you can combine ptychography and reflectometry, you can get three-dimensional reflectivity measure, which means you get a three-dimensional structure of the sample. So what do we do here is, it's a little bit complicated concept. So basically you have a sample here, this is a substrate, then you have a sample. So the real probe coming this way, then this is a scattered specular beam. I think I should shift the image taller a little bit. So, but anyway, you have a lot of diffuse scattering around it. These are all speckle patterns. And I mean, for each incident angle, you will scan this sample because our samples are larger than the footprint of the beam. You do a two-dimensional rastering scans, of the sample, then get a bunch of like ptychography images you can do reconstruction on. So, but the issue is when we do this, we have to, it took us a while to figure out, because in a conventional ptychography experiment, what you measure is in the transmitted geometry, right? So your pattern is right over here. This is where your reference, your Q0 is. But in this case, your Q0, I mean, Q prime zero, I will not call it real Q. The Q prime zero is at the specular, where you do your reflectivity, right? So you have to rescale all the Q values. Okay, by doing ptychography, you get a two-dimensional project image. Now you have to understand what that projection is. It's not a regular projection as where you see using a real probe. It's a projection viewed along this virtual probe direction, which is basically the direction along the specular reflectivity direction. Okay, so now what you do is you change the angle. You do another ptychography. Then you get a different virtual probe, right? Then you keep doing that for a bunch of angles. Then you get a bunch of two-dimensional projected images reconstructed from ptychographies, right? When you put them together in terms of angular space, because you have done the different incident angles, right? Then you create, I will show you in the next slide, then you can create a reflectivity on each pixel on the sample, on each resolvable pixel on the sample. You can imagine that each resolvable pixel, you get a reflectivity. Another pixel on the surface, you get another reflectivity, right? It's like when you do this, you can simultaneously get, I don't know, hundreds of thousands of reflectivities after this scan is done. Right, so the next step to do is to do the reflectivity analysis, which is, everybody knows how to do that. Right, you can get, for example, here I'll show you the reflectivity from pure silicon, pure gold, and some gold film on silicon, you will see oscillations, right? Okay, so another concept here is, because this is ptychography, this is result we got it from ptychography reconstruction. We have an understanding what is the phase, what's the amplitude. In the transmission geometry, we know that ptychography is more or less sensitive to the phase information, I think, because is a path length difference because of the delta variations in the sample, right, in the transverse planes. So so that phase information more or less from delta, but in here, in the reflection geometry, it's just, the phase contrast basically comes from the height variation of the sample. And this is actually exactly why in the reflectivity, you can see these fringes, we call them case-edge fringes. So these are the two different sources of the phase. So we have to interpret the ptychography data differently. Okay, so the T basically here is a reconstructed ptychography. And if you normalize by the virtual probe, we actually get to the conventional in-plane resolvable reflectivity. It's a little bit hard to understand. It took us a while to figure this out. So this is some result. So first I did some simulations to have a bicycle pattern on, it's basically on the silicon surface, some gold bicycle patterns. So different color here, schematically I show here, a different color represent different height. So they can vary from, I think the front wheel is 9 nanometer, the handlebar is probably 50 nanometer on different heights. So so we did a couple of angles here. Well, I'll show you only 3 angles here. So this is a reconstructed amplitude at 1.1 degree, 1.4, and 1.7. They all normalize to the incoming beam and the virtual probe. So you can see that the intensity actually varies. So if you, for each part, let's focus on, let's say this front wheel, because when we made the front wheel, it's 9.1 nanometer height, roughly. So a 9.5 nanometer height. If you focus on the front wheel, you plot the amplitude square versus the angle, that's what you get. It resembles the reflectivity. And from here, fitting reflectivity, you know the height of the front wheel. And again, we have this problem with this oversampling the reflectivity, right? Your film is very thick. You have to do very fine scan in an angle. For example, here with this angular density, we want to be able to fit for the thicker part of the sample. I think it's a handlebar 31 nanometer. You want to be able to tell that with this angular sampling rate. But the good thing is we're not limited by oversampling here. So this is the reconstructed face of the bicycle. You can see different part of the bicycle actually represent a different height. So different part has a different face. So if you put this face together, you will see, for example, for the front wheel, you can see that you have pattern in the face. And also, for this, we can fit this to get, this formula is very simple. It's basically the height path length difference due to the height difference. So you can fit this to get the height of the, the front wheel. As I mentioned here, in this case, if you have thick sample, you want to be able to fit using reflectivity intensity only. But from a face, you still can do it because, here you have a couple of references here. Because in here, if you want to fit the thickness of the handlebars, you can use the front wheel. Here, I think I use the back wheel as a reference. Right? You plot the phase difference of different heights. But as long as the difference is smaller than what your angular sampling rate can resolve, you're still okay. Okay, so then we did some experiments. So we made some double, I think a double Siemens star pattern with 50 nanometer on one side and 30 nanometer on the other side. And these are the ptychography reconstruction at 0.7 degree, 1 degree, and the top is the amplitude, the bottom is basically phase. And you can see as the changes in angle, the phase of different region keep changing. So by doing that, you actually can resolve the height. I didn't plot the reflectivity, the amplitude here, because we don't have enough oversampling for reflectivity to show here. But when the beam come back, we're going to do more experiments here. But I can tell you that although we were not able to resolve the 50 nanometer thickness, but if we use this relative phase method, we can tell all different parts, the height of different parts on the pattern. Okay, so of course you probably already realized that I didn't do in-plane rotation. It's a great incidence. So everybody do great incidence, you have isotopic resolution in the plane. We have to admit, it's like in a ptychography, transmission ptychography, you don't have resolution along the beam. Here is the same thing. You don't have enough resolution along the beam, but on the sample surface. But you still have a little bit of resolution because we're coming at a gradient angle. But that resolution is pretty bad. It depends on the incident angle you use. For example, for 1 degree incident angle, you get a 60 times worse spatial resolution along the beam than transverse, to the beam. So how to get it back? The idea is simple. You have to do in-plane rotation, called that tomography. Right? We have done some simulation studies over here, and when the beam come back, when we have a sample ready, we're going to do the experimental demonstration. Okay, so far, I talk about so the reconstruction algorithm we use for CDI, for ptychography, they are all based on conventional algorithm, which you only deal with a single scattering event, which means kind of kinematic scattering or Born approximation. I haven't talked about dynamic effect, but of course, at great incidence, a lot of dynamic scattering effect. So, one of the famous way of dealing this dynamic effect, the great incidence, is the DWBA theory, where you can have 4 different scattering events for different channels in the sample system. So where you have first, for example, first you have incident beam, then have scatter beam. This is the conventional way of dealing, scattering, this small angle ptychography CDI. But you have some other scattering events might happen at some probabilities. For example, here the beam can be reflected by the substrate, that's scattered by the sample. This is the beam scattered by the sample, then reflected by the substrate. That is a combination of these 2 events. So the Lloyd mirror effect that I just mentioned is basically the event 1 here plus the event 3 over here. This Lloyd mirror effect. Of course, you can have other effects, for example, 1 plus 2. I don't know, 2 plus 3 probably not possible. I don't know, but it's all depending on incident angle because each term has different weight. Okay, the second term have the weight of the Frañó reflection coefficient in front. That depends on how strong the substrate reflects the incident beam. And this is another Frañó reflection coefficient on the excitant angle side. So there are a lot of things you can play in experiment because you can change the incident angle. You can go high incident angle, low excitant angle, low incident angle, high excitant angle, both low in high incident angle, excitant angle, both high. So the ptychography CDI I introduced before they are basically on the first case where both angles are high, because that time we don't know how to deal with the dynamical, how to do reconstruction with the dynamical effect in there. But even now we don't have a complete solution, but we are closer. So to deal with this thing, there are a couple of ways. First, this is conventional DWBA, and conventional DWBA is basically treat the substrate as a perturbation to an electric field in the space. It's only deal with the vertical direction, doesn't deal with the horizontal direction. But it's okay if you have a regular GSAC sample where all over the sample surface, everything is random, right? On average, you smear everything. So you don't have an in-plane variation of the electric field. But if you have like a well-defined sample, for example, here, lithography samples or semiconductor samples, your in-plane is not complete random. You have structures in there, with some orientation in there. So this conventional DWBA fails. So in here, basically, you have to deal with the electric field variation or perturbation in the plane, which is caused by your sample. So we actually introduced this finite element DWBA, where you discretize the sample in 3 dimensions in both directions. Then you calculate the electric field in each big voxel here, we call voxel here. Then you calculate the form factor or structure factor of each voxel, then add up them together. And you can imagine that easily for this 2.5 or 360 micron, with the wavelength of X-ray, you can imagine how large the number of voxels is going to be. It can be millions of voxels. It's extremely slow. This is not efficient. Although it reproduces the data very nicely, but computation-wise, it's not efficient at all. So then we try another method, which is multi-slicing plus Frañó propagator. So some ptychography community, dealing with the thick samples, or maybe with structures on the beam, they use a few slices to do that. But in this case, we are dealing with footprint of several hundred micron. So in principle, we're going to have, I don't know, hundreds to thousands of slices. So, but anyway, this is another problem for forward calculation. We can simulate the experimental data very precisely. Actually, this is exactly the method that we use to simulate this, bicycle pattern, for our simulation studies, for simulated reconstructions. But for experimental reconstruction, for the reconstruction, image reconstruction, using this multi-slicing to take into account the dynamic scaling factor, we are still working on that. Okay, so but there are some progress already recently for the reconstruction with this dynamic effect for smaller samples. For example, the DWBA plus CDI in tomography doing in-plane rotation, and Suni Sinha's group in UCSD has developed the algorithm last year. It works for small samples. And Jeff Donatelli here at the LS, and he actually using his uniform iterative phasing method to tackle this problem. We had some progress in there. I don't think I have time to talk about it. Okay, so since I'm an experimental scientist, I want to talk about experimental beamlines. Hopefully you're still awake. I talk about too much theories here. Anyway, so I work a little bit for XPCS, but I'm mainly responsible for this CSSI beamline. So this beamline is still under construction. So we had a front hatch, we got a wide beam mirror here, we got a double crystal monochromator, so our energy range will be 6 to 25 keV. We have 3 focusing components to deal with different beam sizes and the different energies. So we have basically 2 translocators in a zoom configuration, and we have KB focusing just before the CSSI sample station. And this beamline is also compatible with conventional GSAX, GWAX measurement, and also gradient and XPCS measurement. Yeah, you probably noticed that after the experiment include, you have long tube. This is called the grand tube. This is where we put our detector in there, IGER 16M in there. And we need, because we're doing image experiment, we need to try different oversampling rate. And also for XPCS, you need to try to maximize the contrast depending on beam size. So you have to move the detector back and forth. So we have a grand tube, which is, I think, a 20-meter long, 3-meter in diameter. You basically can drive your car in there. All right, so, okay, so yeah, there's some specs in here. Yeah, so our beam size 0.5 to 2 micron for CSSI. It's a little bigger for XPCS and even bigger for conventional GWAX. Our flux after upgrade will be 10 to the 12th photon per second up to 10 to the 13th photon per second for 2 to 3 coherence modes. I mean, you can, coherent mode, right? So you can open the slit if you want for XPCS, which is more like a photon flux eager experiment. So you have to, get more flux. So basically what you can do, you can sacrifice the contrast a little bit by opening up your coherent slit a little bit. You get more coherent modes in there. Yeah, so I don't think I should talk about this. Yeah, for the CSSI, the most of the difficult part we think is not the beamline itself, it's the sample control. Because you can imagine that you need to do ptychography scans at a reflecting geometry. So you have to control the 6 degree of freedom, the sample X, Y, Z, and all 3 angles. And also you have to deal with a lot of like motion couplings because you have a beam there. You have to be able to make sure that your rotation center is always in the beam. So it turned out that we have a stack of 17 stages to control this. So I don't want to talk about this, it's a mess here. Yeah, so this is some pictures we took from the Grand Tube, which was installed half a year ago, probably 8 months ago. And this is from the back view before we put this dome back. Before we put this dome in the back, so this is what you see. So this we have a carriage here. We have 2 detectors on it, Pilatus, not Pilatus, Eiger 16M and MMPAD in there. MMPAD has the bigger pixels and high dynamic range. So it'll be helpful to look at more or less the direct beam and also the XPCS, hopefully. Yeah, so I have a movie here to show the Grand Tube. Okay, doesn't work. Yeah. Very chunky. Okay. I think that's end of my talk. Thank you.
Thanks. All right, questions?
Beautiful talk, Bob. In your bicycle example, I think the analysis you showed, the phase term was just related to the height difference.
Yeah.
But it's a thin film and there's different materials, so you should have a Fresnel coefficient, and that's what's causing those ripples
Exactly.
in the gold on silicon that you showed.
Yes.
I think the later methods that you described should capture this, but it seemed to be missing from what you were saying.
Yeah, I know what you mean. Exactly. What actually the simplified experiment. Actually, the phase comes from, if we have a flat surface, the phase purely comes from Fresnel reflection. But you have layers on it, you can calculate, the overall phase after, interference. That can be calculated. That is exactly how people calculate using Pareto's method. And what actually is the simplified version that, it's actually, coming from the phase. You first have to calculate Fresnel, reflection from your reference, which is substrate, and your Fresnel, or basically the phase from the gold, then take the difference. Because what we measure here is not the absolute phase, it's the difference, phase difference.
And it's height dependent, I imagine.
It's height dependent, also material dependent too. You can imagine different material going to change that.
Phase
Yes, yeah.
shifts a bit.
Yeah, and what you show you here is on not embedded film, it's just the pattern on the surface. But you have embedded film, this technique also works. We have simulated data. Let's stop you here.
Okay, any other questions? So for if, go ahead. No, go ahead, I'll ask later on. Please.
So the level of complexity that you have to take care of is very high because you have, now you know everything, you have the ground truth that helps you with simulations and whatever. If you have an unknown sample with a known coefficient, with maybe bubbles, with anything inside, how can you take care of everything, plus the dynamical part, plus everything else?
That's extremely good. That will be our ultimate goal, Completely, you don't need any model, right? You don't need a prior knowledge, but in reality, that never happens, right? So for every sample you put a beam, at least you have to know roughly, right? You can use optical microscope, for example, right? Or CM something, you sort of know what the pattern looks like roughly. And I have to say, dynamic scattering is another difficult part that we have to deal with. At this moment, we don't have a mature. We have some algorithms to do CDI with dynamic effect in there, but we don't have the ptychography algorithm that can handle with dynamical. I mean, in principle, easy, just do multi-slicing, you do iterate, but it's considering this computation resources, we cannot handle this at this moment. But I agree with you. When your question is our ultimate goal, I would say this is probably 5 to 10 years goal we are having right now. Please.
How long does it take for
Okay. Do you want to give a guess? 10 to the minus 2, because this is detected. It doesn't have to be ultra high.
maybe hours then?
20 minutes.
20 minutes? Wow.
20 minutes, you can start experiment. But to get to 10 to the minus 3, it's going to take maybe several more hours.
My second question was, what's the control for your 17 stack station?
Okay, that's hard. So just I want to say this is not okay. Our engineers are really brilliant. They stack up. We talk to different vendors, figure out differently. This is a combination of Kozu, whatever, Smart Act, some customized flexure stage, cube, all different things. I want to let you know that we also have metrology, 3 metrology systems there. 2 cap sensor metrology system and 1 laser interferometer there to monitor sample motions.
Can I ask you, what is the safety protocol for closing this? I mean, there must be some big.
There must be some, I think the safety people are still working on that. That's not my problem.
That's the emergency.
There are protocols of open the door and make sure nobody inside,
Exactly.
and the oxygen, all different things,
All right, any other questions before we close? If not, let's thank all the speakers again. Okay, we are running a little bit late. We were supposed to start the break at 2:40 and start back again at 3:05. It's already 3. I say 3:15 because we would like to keep the time at the second session for our discussion, which is an important point. And then also we have a group photo. The photographer has been scheduled, I believe, and then we have to be there at the session back again at 5:30. So let's be mindful of the time. So let's start back at 3:15.
So, now it's 10 minutes. We're 10 minutes short. Okay, it should be 3:45. I'll try and have it. Okay, I think we're trying.
Very nice. I was you have like the student, then you like every and every and you see in fact the chasing long time when they started studying that holography they were getting people very much.
Finally, it works. I think it's not just a concept.